everybody. Fantastic to see so many of you here. When it was such a cold night and rain, I thought, maybe people are staying at home and watching the television. But I hope to entertain you tonight with a story actually about outer space, where it is also very cold. But maybe I can tell you a little heartwarming story about how in this very cold environment you can actually make molecules, how you can build other planets, like maybe something that looks like our Earth. And certainly we're going to show how to make cocktails in these clouds. So stay tuned for that. Good. So astronomers are not the only people who are interested in the origin of stars and planets. Where do we come from? This is a question that excites, a lot of people. I mean, given the fact that so many of you are here, this must also be of interest to you. And you see that actually throughout different kinds of art. So one of my hobbies when I'm not doing astronomy is actually looking at astronomy and art. And you see sort of this interest in the heavens, in the stars, in how we were made. You see that also reflected in various paintings. You can just go across the globe. I mean, of course, in the Netherlands, we have Vincent van Gogh with his Starry Night, that you see here, the Big Dipper. But if you go to the other side of the world, in Australia, there the Aboriginals actually have a Milky Way dreaming. How many of you have been to the southern sky? Yes, and so you know that if you look up there, you have this fantastic Milky Way that you see there. Well, here you see the Milky Way with the spiral arms, and this is the Pleiades, the seven sisters that are sitting here in the heart of the Milky Way because this old man Orion is chasing them. And you see that's on the southern sky because Orion is actually higher than the Pleiades, which is just opposite of what we have over here. Here you go to the Pacific Northwest in Canada. There we see actually first Raven putting the sun out of a black box and putting it on the sky. That's their story of how our sun originated. And here, stars from Kandinsky, a very nice painting. Actually, you see here also these stars originating in a black box, in a black circle, in a black cloud, actually. And this was painted well before even astronomers knew that stars don't have eternal life, that stars are actually born and that they also die at some stage again. Good, so this is just to show you that there's a lot of fascination on this topic out there and that it's also inspirational for various artists. And maybe we'll hear a little bit about that in the music later this evening. So one of the most important discoveries that happened over the last 20 years is the discovery of planets around stars other than our sun. Of course, we know the planets in our own solar system, around our star, the sun, but even though it was speculated for centuries, the first scientific proof that there were these exoplanets, planets around other stars than our sun, only happened in 1995. And one of the ways in which astronomers have discovered them is that if such a planet passes in front of a star, then you see a tiny, tiny little dip in the light curve, and that's how you can detect them. Just like Venus went in front of the sun not so long ago, a few years ago, then also we saw this tiny little dip in the intensity of the sun. And so thanks to this technique and also other techniques, we now know that there are just zillions of planets out there. More than 4,000 have been identified, but statistically, on average, we now know that every star has at least one planet. And these planets come in various sizes. I mean, some of them are as small as the Earth, some of them are as big as Jupiter, but it turns actually out that the majority of them are of a kind that we don't have in our own solar system. They're sort of super Earth or mini Neptunes, a few times the mass and size of our Earth and a little bit smaller than Neptune. And so that has made all of these age-old questions, such as where and how are stars and planets born, how unique is our solar system? That's still an important question. We know that there are other planets there, but are these planetary systems like our own? We haven't found a second one yet. And which of these planets could be habitable? That's, of course, for the origin of life question. So, summarizing sort of what we would like to address tonight is basically how were we formed, some 4.5 billion years ago. And so we can do that by looking remotely at other forming planetary systems. We can also look at the record of the formation of our own solar system. And we can do that through meteorites, which fall on Earth on a daily basis still, and that tell us something about the history of our own inner part of our solar system. And we can also do it by looking at comets, which tell us a story about the outer solar system. So both meteorites and comets are messengers from the early solar system, and we'll look at one particular comet that was visited by the Rosetta satellites at the end of the lecture. So just to remind you where we actually are in our galaxy, our Milky Way. So a galaxy is basically the collection of some 200 billions of stars, and this is an artist impression, but based on real data, astronomical data, as to what our galaxy, our Milky Way, actually looks like if we would be able to look at it from the top. So here's the center of the galaxy, and here's our sun. So our sun, the star, is just one of these 200 billions of stars. And our Milky Way is again one of several hundred of billions of galaxies in the universe. So that shows already that, you know, we live on this small planet, a tiny planet that is circling a rather ordinary star somewhere in the outskirts of the galaxy, of which there are several hundred billions in the universe. So are we unique? We don't know yet, but it certainly shows that there is a large chance of finding other planetary systems that may look like our own elsewhere in the universe. All right, so where does this all start? Where do these planets and the stars come from? Well, it all starts in the clouds between the stars. So if this had been a beautiful summer night, like we've had so many over the last month, you would look up and you would see the stars. And maybe a few planets. Mars has been very bright lately. But few people have actually asked the question, what is in between the stars? Well, that region is not empty, but it's actually filled with a very, very dilute gas. And it's inside this gas that actually stars and planets are being born. Now, this is a constellation that many of you will recognize. Orion, yes, I hear that already. So here we have the Hunter, here is his belt, here is his sword, and there is the Orion Nebula that is actually one of the most active star-forming regions in our own galaxy. So this is a modern image of it taken with the Hubble Space Telescope. And so what you see here is 4 very bright stars, the trapezium stars. You see a bar, and then you see this gigantic nebula. This is not the part of this gas that we are interested in, because this is very hot gas, maybe some 10,000 degrees. And what you see here is beautifully the radiation from hydrogen atoms that are actually recombining, so going from ions to neutrals, and they emit then red radiation. So this is not what we're interested in, but what makes these images so beautiful. We are interested in these dark parts that you see over here. And in fact, if you go to the next image that you see over here, then again we see, then you see here these clouds, these dark clouds now, in front of a bright nebula. That's why we can see them so nicely in this particular case. And you see that they are some of the biggest structures that we actually have in the galaxy. They can be up to several light years in diameter, and they can have masses up to maybe 10,000 or maybe 100,000 solar masses. So in principle, these clouds have enough material to form another 10,000, say, new stars. They won't do that. They do that only with an efficiency of a few percent, but it shows already that there's quite a bit of material available there. Now, why are they so dark? They are so dark because they contain not just gas, but also tiny, tiny little dust grains. So think of the sand. You saw this image all the time of a beach with sand. Think of that sand, but then 1,000 times smaller, consisting of silicates, basically, and also some carbonaceous material. And as you know, small particles like smoke, you can also think of smoke particles, they absorb and scatter the light. So if smoking was still allowed in this room, then you would know that you wouldn't be able to look very far. It would look very dark very, very soon. And that's what is happening here as well. So these dark clouds are actually, the birthplaces then of the stars, and it's also where we find the molecules. So these clouds contain by mass 99% gas, and that's mostly hydrogen. And about 1% by mass is then this dust, which are these very tiny silicates and carbonaceous material. It's very cold out there, just 10 degrees above the absolute zero, minus 260 degrees if you think of it on the Celsius scale. And the density is also very low, only 10,000 particles per cubic centimeters. Now to give you an idea, here in this room, it contains 1 cubic centimeter contains about 3 times 10 to the 19 particles per cubic centimeter. An ultra-high vacuum laboratory on Earth still contains 100 million particles per cubic centimeter. So what an astronomer calls a dense cloud is still much more anti than anything that we make here on Earth. So that is also what makes it such an interesting laboratory, physical chemical laboratory. I started my career in chemistry, and so this is for me the ultimate laboratory because it is so special there. Good, but how do we actually study what is happening inside this cloud? Because seeing a dark cloud is nice, but we don't learn anything except that there is a cloud. We really want to look inside, and to do that we have to put on different glasses. So we have to look with light that is different from the light that we see with our own eyes. We have to go to longer wavelengths, to infrared wavelengths, and even longer to millimeter wavelengths. And then that absorption and scattering from the dust grains is much less, and we can actually look through the clouds and see what is actually happening inside. So here's an example of such a dark cloud. This is actual data from the Spitzer Space Telescope, and we are zooming in here on one of these dark clouds. And what we see here is actually a young star that is being born inside this cloud when we go to the infrared wavelength. So here we see in the optical wavelengths it's just completely dark, but now we zoom in and we go to longer and longer wavelengths. Now we see that actually inside this dark cloud there's a young star that is being born at this moment. It already has an outflow, it's pushing away its natal cocoon, and we end up then eventually with a new star there. So what kind of telescopes do we have available? So we have space telescopes in space, and those are very powerful because they are not bothered by the atmosphere, our own atmosphere. Our own atmosphere is, of course, full of water, as you have testified today. It's full of CO2, etc. So if we want to see, say, water in space, we cannot do it from Earth because the only thing we would see is water in our atmosphere. So we have to really go above space in order to see that. And especially here, the Herschel Space Observatory, that was the biggest astronomical observatory ever, larger even than the Hubble Space Telescope, a diameter of 3.5 meters. And that had an instrument on board that was very well suited in order to study water in space. And so we learned a lot from this Herschel Space Observatory. And just to show you how technology can progress over the years, this is an image that we would have from one of these star-forming clouds at these long wavelengths. This is at far infrared wavelengths, around 100 microns or tenths of a millimeter. Just a really poor image. But now, this is the kind of images that Herschel gives us, and it's just fantastic. It's almost as a beautiful painting here, what you see. But all of these little dots that you see in here are actually young stars that are currently forming inside this dense cloud. Now, we also have telescopes from the ground. We have optical infrared telescopes, and especially the European Southern Observatory. That's a collaboration between the different countries in Europe in order to put telescopes in Chile. In this case, 8-meter class telescopes in northern Chile. and that is where we write a lot of our proposals in order to get observing time on these kinds of telescopes. And in the future, even larger telescopes are being envisaged, such as the ELT, the Extremely Large Telescope. Not very original names here that they have. But that is going to be close to 40 meters, and that's being built actually at this very moment. And then my dream machine is actually the Atacama Large Millimeter Array, ALMA. This is a worldwide collaboration between Europe, North America, and East Asia to put together about 66 telescopes on a high altitude plane in northern Chile. That was inaugurated in 2013, and that array is actually particularly well suited to study interstellar molecules and the birthplaces of stars and planets. This is just to show you the logistical nightmare that you have if you want to build such an array at a very remote place, with components coming from all different parts of the world that have to be brought to Chile, to be assembled, then put on a gigantic truck, and then put in the array on the high side. And it is indeed a high side because we are actually located at 5,000 meters altitude. This is on the border of Chile, Argentina, and Bolivia. Right at that border, there's a gigantic plateau, the Chasnantor Plateau, and that is very well suited for this array. But, and this is how it is now, actually, it is actually literally and also figuratively a breathtaking experience to be there, because I can assure you, it takes a while before you can get adjusted there. All right, so that is how we do our observations. Now, a little bit of chemistry. So what do we actually see here? Well, this is not like the periodic table that you had on high school. You see actually that it looks a little bit different. Hydrogen is by far the most abundant element. That was actually made already during the Big Bang. Big Bang also produced helium, 10% with respect to hydrogen. But as we know, helium is not a noble gas, so it's chemically not very interesting. The chemically interesting elements, the elements that we need in order to make life, those carbon, nitrogen, oxygen, those are actually present at a fraction of a promille. So a few times 10 to minus 4 with respect to hydrogen. And so if you go to other elements in the next row of the periodic table, we find even less by an order of magnitude. So what we have here is this very cold, very dilute gas, mostly hydrogen, just here and there an interesting atom. And so the chemists told the astronomers, don't even bother looking for molecules because you won't find them. You know, there's no way that you can find molecules under these conditions. Well, fortunately, the astronomers didn't listen. They started tuning their receivers. And by the early 1970s, they started to find one molecule after another. And here is just one of these fingerprints, actually, that we have from such a star-forming cloud. This is a type of what we call spectrum that can be taken now in just 30 seconds on one of these powerful telescopes. And what it basically says is that every molecule has its own fingerprint. Due to the laws of quantum mechanics, every molecule has a discrete number of energy levels, and so it can radiate only at very specific frequencies. It's a little bit like, you know, when you buy a product in the supermarket, you see that it has a barcode. And so that barcode actually tells you the product that you have. Exactly the same here. So these are uniquely ascribed to dimethyl ether. We see here methanol. Well, those of you who know your chemistry, this is SO2, sulfur dioxide. So you see already that in this way we can identify lots of different molecules. And so this is just an example of the rich variety of molecules that have been detected. Some of them are simple molecules like carbon monoxide, but some of them are already quite complex ones, such as this little sugar that we have over here. Dimethyl ether, cyanides that we have here, benzene, And of course, this molecule, which is very important ingredient for tonight's proceedings, which is, of course, ethanol, that is definitely present here. So one such cloud as Orion has enough for 10 to the 29 bottles of whiskey. So no shortage in space. So if he runs out, you can actually go to a cloud and tap a beer there. Although it is less than 1% with respect to water, so that is not so good. We actually find more complex molecules, also thanks to ALMA. We see sort of branched cyanides now, which are more starting to be characteristics of amino acids. We have the first chiral molecules that have been detected that may tell us something about origins of life. We also see some very large carbonaceous molecules actually in these clouds. In these cases, we don't know the exact molecular composition, but only that they are present as a class of clouds. These are these polycyclic aromatic hydrocarbons, which are well known because you have them in the exhaust of your car, for example, or if you leave, beef too long on the barbecue, you also get you make a lot of PAHs actually in that way. Foudarines, C60, C70, these buckyballs as they are called, the third stable form of carbon on Earth. Actually, their discovery was inspired by this interstellar chemistry, and they have now also been detected in space. But I actually want to talk about here is not just what we see in the gas phase, as vapor, basically, but also what we see as ices. Because these tiny little dust grains, these silicates, they actually act as a deep freeze. So when an atom or molecule from the gas arrives on this silicate grain, it can actually stick there. Just as on a cold winter night, like you may have in a couple of days, that it gets very cold, you know that actually the water from the atmosphere freezes out and make a little icy layer on your windshield. Same here, you can actually freeze out various atoms and molecules, and then on the grain surface actually a different type of chemistry can occur than we have in the gas. And very importantly, we can actually turn oxygen into water, we can turn carbon into methane, nitrogen into ammonia, and these are all kinds of reactions that don't happen easily in the gas phase. And in fact, we can turn carbon monoxide into methanol, which is actually the simplest form of alcohol. We also find some CO2 in these ices, so these are the bubbles, of course. So we can say that we have literally made an ice cocktail here in space on these tiny dust grains, and that also the alcohol is literally on the rocks here in these regions. Good. Right, so how do we actually make water? Well, this is actually something that we have been working on quite a lot, both from observations point of view and also in the laboratory. And this is a nice animation that was made. So basically, maybe once a day, we are zooming in on one of these cells. Yeah, there, once a day, a hydrogen atom lands on the grains, it finds another hydrogen atom, goes off again. It may also find an oxygen atom and make a water molecule then. So there, yeah, we have made OH. Now we're making O2. Keep that in mind. Now we're going to, because we're going to see that later. Now we've made hydrogen peroxide. And now we have made water, actually. And now we're going to do a fast forward, and some 10,000 or 100,000 years, we can easily do that in space, that's nothing. And that's how we actually make this icy layer onto this tiny dust grain, and now we have this ice-coated dust grain. So this is actually the mechanism by which most of the water here on Earth was made. The water on Earth was made already in the cloud, out of which our own solar system formed. The bulk of the water here on Earth was made already 4.5 billion years ago. And so we can also actually say that, as one of my colleagues put it, that the water here on Earth is actually older than the sun itself, because you first need to collapse this cloud in order to form the sun. So when you take a sip of water, as I now do, then you're actually drinking these 4.5 billion years old molecules. Good. Right, so we can actually quantify how much water we have. From the strengths of the signals that we have, these are detections that we made with the Herschel satellite, the HiFi satellite, and from the strengths of this signal, we can actually count how many molecules there are in this case, a planet-forming disks, and we can see that there is enough water to form a new solar system, about 6,000 oceans of life. Now, this kind of research has not gone unnoticed. Even the Big Bang theory got its attention. You see here that both the water and the ionized water that was studied by HiFi made it actually onto the whiteboard over here. So, where are we so far? What we have seen is that interstellar clouds, these very tenuous cold clouds, they actually have a surprisingly rich chemical composition in spite of the cold and tenuous conditions. We've also seen that water and complex organic molecules are found around nearly all the forming stars. So we can just point our telescopes to different forming stars and we always find nearly the same composition of water and these organic molecules. So in that sense, the building blocks for prebiotic material are certainly widespread throughout our galaxy. So now we're going to actually look at how a new star and planetary system are formed. So now we're going to go back from chemistry to physics. So here we have our cloud, and for a long time, maybe millions of years, it can actually be stable. But then at some stage, gravity takes over. And when gravity takes over, it basically collapses and it starts to form a protostar at the center. Because the cloud always has a tiny bit of rotation, it means that not all the material can fall in radially, but a fraction of it actually ends up in a rotating disk around the young star. And it is this disk which is actually so important because that is where we can start to form planets. So let's look at a little animation. So this is actually taking data from the Hubble Space Telescope of the Orion Nebula. So we're going back to Orion. But now this is a movie that transforms our two-dimensional image on the sky into a three-dimensional movie so that we can actually travel through it. So here you see again these bright stars. And now we're going to go actually on a spaceship, not to planet X31, but actually maybe to another planetary system. And you see here all of these protostars actually here in this nebula, all of these young stars that are still embedded in their cocoon and in which they can then form a new planetary system. And now we're going to zoom in actually on an animation here of one of them. So now the UV radiation from the stars and this jet can blow away the surrounding material. And what we are left with is then this young star surrounded by this rotating disk of gas and dust. And that is actually where we will start to form planets. Now, we have a little problem, because these planets, this is an artist impression, these planetary disks, the protoplanetary disks, these disks are actually very tiny. If I would put it on this scale, so they're about 1,000 times smaller than the cloud. So if I would put it on this scale and try to see it, I would really need sort of a magnifying glass in order to see it, because it is so tiny, these disks on these scales. So pre-ALMA, we only could look on sort of the large scales. We could only study the cloud as a whole, or the collapsing core as a whole. But now with ALMA, we can actually zoom in on these tiny little places there and see whether there's a planetary system forming there. And this shows the power of ALMA. ALMA can now do in 1 minute what took pre-ALMA with some pioneering arrays, maybe a full night of observations. You can point ALMA at all these forming stars that you see in a region like Orion or any of the other star-forming clouds, and you could just detect all of these disks around them, actually. Some of them are big, some of them are small, but we can, from these kind of images, actually get both their size and we can get their mass. And if we do that for hundreds of sources, then we find that the majority are indeed detected here in the thermal emission from this dust. And so to make a long story short of a lot of work that has been going on in the last years, we find that nearly all of the young stars are actually surrounded by disks, and that the sizes of these disks are actually comparable to that of our own solar system. Moreover, the masses of some of these disks are enough to form a solar system. And what do we need to form a solar system like our own? We need about 1% of the mass of the Sun, say 10 times the mass of Jupiter. That's what we need to make our own solar system. So some of the disks, maybe 20-25% have enough to do that. The others have at least enough material to form an Earth-like planet. So this tells us that indeed the ingredients for planet formation are also common, and that is consistent with the fact that we see now statistically that almost every star has a planet around it. Back to a little bit of art. So this is one of my favorite paintings that is from our collection. That is an English engraving. It dates from 1798. And it shows, it's called Universal Solar System. It shows our own solar system as it was known at that time. 7 planets were known at that time. But it showed the possibility that these other planetary systems would be very different from our own. Some of them planets closer by, some of them further away, some of them many planets, and some of them just a few planets. And also you see some comets actually in here. Now this is exactly, of course, what we're now finding, this enormous diversity in planetary systems. Some of them with very big planets, some of them with very small planets, and some of them, many of them with planets in between. So how do these different planetary systems form? Well, that is actually exactly the answer lies in the past, how they were formed, namely from these circumstellar disks. And so there are a few concepts. This is a topic that is very much being worked up at this moment. How do we form these planets? We have a few concepts that I will discuss. One of them is the concept of snow lines. Snow line you can see here beautifully in nature. You see here a snow-capped volcano, and you see that at a certain altitude the temperature becomes warm enough that it goes from ice to gas. And so that's an example of a snow line in nature. Now in our protosolar disks, there's also a temperature gradient. Close to the star, it's hot. Far away from the star, it's cold. So here are grains, and the larger grains, which we will call planetesimals, are ice-covered. And so they will have a lot of ice. Here they are bare, and so they are just rocky. Now, water ice actually helps the sticking of small particles to make larger particles. And so it's maybe no surprise that our large giant planets in our own solar system, like Jupiter, like Saturn, that they are formed actually outside where the ice line is in our own solar system. Has been a theory for a long time, but now we're starting to see also this phenomena in other regions. So let's look at a small animation actually from, let's see if that wants to play. Actually of how we think that these, here we have our protoplanetary disk. And now we're going to zoom in into it, and we're going to see these little dust particles. And we're going to actually collide them, and we're going to grow them to larger and larger. Here we have these grains. So they all, of course, in this rotating disk, but once in a while they bump in each other. If they bump too powerfully, it will all, they will shatter apart. But if they collide rather gently, then you grow larger and larger and larger particles. And this is how, bit by bit, we have gone from these micron-sized grains to maybe something that is as large as a kilometer in size. Do we see some of that happening now in other planetary systems? Well, perhaps we do. Because if the object is large enough, it acts a little bit like a snowplow, and it will actually excavate rings in these disks. And this is an iconic image now from ALMA, in which we actually can see some of these things happening. I see actually that I have my own. I think this is the primordial soup, isn't it? Very appropriate. So this is actually very good. This is actually the region where we have this. Now the orbit of Neptune is right around here. And we see these rings, and this could be the signature that in these disks actually planet formation is ongoing at this very moment. In fact, we are in a completely new era thanks to ALMA of what we call observational planet formation. So we see here again, this is this one iconic disk that we've seen before, but here also another one on this Earth scale actually. So 1 astronomical unit is the distance from the sun to the Earth, and we see again a gap there. So there could be a planet happening there as well. We see spiral features, we see very asymmetric peanuts, which we think are dust traps, regions where at this very moment comets are being built. And so this is the kind of new data that we are now working with in order to see sort of planet formation and action in these other planetary systems. So very briefly, planet formation, we start with these very tiny grains. We go to larger regions, like the larger bodies, like the comets. Then we go to lunar-sized objects, like or Mars-sized planetary embryos is what we call them. And then finally, through collisions, they make something that may or may not look like our Earth. Now let's look a little bit at this stage, because this is the critical building stage of a few kilometers. And that's exactly the size of comets. And of course, we can see comets in our own solar system. Some of you may be old enough to have seen Comet Hale-Bopp in 1996. It was gorgeous on the sky, beautiful. I can't wait to see another comet like that again. But we've also traveled to comets. The Rosetta mission has actually visited this comet, this little duck that we have here. This you see it over here. That is probably made of two pieces of these building blocks coming together. We have landed on that comet, and we've also looked at it in quite some detail. Here are some images of this taken by the spacecraft. This is actually a selfie where you see the spacecraft with the comet actually over there. Here you see some jets. It's actually losing 2 glasses of water per second at this time. Maximum, when it was as closest to the sun, it was about 5 liters per second. This was the landing site on which it landed. So beautiful detail what you see here actually through these fantastic images. This is about 1 kilometer in size. You see large boulders, but also dunes, cliffs, everything is there on this one. And this is the proof that we actually landed there. You see the tripod actually of the lander. The only problem is the harpoon didn't work. So it landed not just once, but it landed actually 3 times. And it hopped to a place a little bit in the shade, which made it a little bit more difficult to do its measurements. But fortunately, Rosetta also, the orbiter that didn't go to the land, but the orbiter around the comet, which traveled with the comet for about 2 years at 10 kilometers distance, that actually had a very good nose, a very sensitive mass spectrometer, and it could just sniff what was coming out of this comet. And what did it find? It found some of these same molecules, our same cocktail actually there. We found water, CO2 again, methane. We found alcohol there, but then there was the surprise. What did we see there actually? What is this? Why is there so much of it? Oxygen, molecular oxygen. This is something that we need for origin of life. And this is because it was such a very sensitive spectrometer. Previously it was confused with sulfur and with methanol, but now people could see that it was really all oxygen actually contributing to this signal. And so this is already an indication that these building blocks, because we make these planets out of these kind of building blocks, that they contain already quite a little bit of oxygen as well. In fact, you can look at a complete zoo of molecules that you find there. Many of them the same molecules that we also find in our interstellar clouds. We even find glycine there, the simplest amino acid. Something that we haven't seen in interstellar clouds yet, but glycine is seen here already. We see interesting sulfur-bearing molecules. Here is the molecular oxygen, cyanide, chlorides, all kinds of propanol, ethanol is also there, present, our cocktail, but going even all the way to pentanol in this particular case. So a very rich chemistry that is present in these building blocks. Now the difficult part. Can we bring these molecules intact on a young planet? So this is really the difficult part that people are wrestling with, that we know also from all the craters on the moon that there were lots of impacts actually in the early solar system. And we have proved that comet-like bodies or icy planetesimals must have delivered at least some of the water on Earth, because we find that from the amount of heavy water that we actually have present in these regions compared with the amount of normal water. The similarity actually indicates that, that these icy planetesimals from our outer solar system actually were important in delivering some of this water on Earth. But whether you really survive these impacts, if they were too powerful, then just everything is obliterated and you have to start from scratch again. We know it happened in our own solar system, at least on Earth. Could it happen in other solar systems? The answer is certainly possible. We have all the ingredients available. We probably need to go to a place where water is liquid. So we have seen only water as gas and as ice. So it's gas if it's very close to the star, it's ice if it's very far away. But under the high pressures that we have on the planet, water can also be liquid. And as long as we're in the sort of the habitable zone, if it is warm enough, not too warm, not too cold, like Earth is here, and Mars also a little bit, then we have another condition actually for the origin of life. Now, where this habitable zone lies depends actually on the properties of the star. Our sun is a normal star, but there are many, lots of smaller stars actually, where the habitable zone would be closer actually to the parent star. What people are then going to look for is these signatures in the planetary atmospheres, not just carbon dioxide, which you see in both Venus, Earth, and Mars, but signatures of molecules like water, of oxygen, of O3, ozone, of methane. You need sort of signatures of sort of a disequilibrium chemistry that could be signatures of life on that planet. What exactly is a biomarker is a subject of a lot of debates in the scientific community at the moment, but certainly some combination of these species, maybe some nitrogen oxides is needed in order to verify that. So, we've talked about cocktails, now we're talking about beer, Trappist. This is actually a new planetary system that is discovered just last year by, of course, a Belgian astronomer, Michel Guillaume. And they called them TRAPPIST-1. There's also TRAPPIST-2 now, but TRAPPIST-1 is the most famous one. 7 Earth-like planets, very close to the mother star, and 3 of them in the habitable zone. So could you be alive there? This is what we're going to find out with the next generation of telescopes, like the James Webb Space Telescope, like these extremely large telescopes. Maybe even life on the nearest planet. Our closest star to us, just a few light years away, is Alpha Centauri, Proxima Centauri. And a few years ago, a planet was discovered actually around that star. And this is an artist's impression of Proxima b, as it is called, of what this planet could actually look like. And so it's really, using sort of the power of this next generation of telescopes that we can start to address this question, are we really alone? So, I leave you here with this summary. I hope to have given you a taste, literally, of what the building blocks are of new stars, of new planets. Whether, we have the ingredients for life. The answer to that question is yes. Whether life originates is, of course, a very different question. That's actually a question that you have to ask the chemists and the biologists. But certainly the ingredients are there. And so all of this provides us with more insight as to how we were formed some 4.5 billion years ago. Thank you very much for your attention. Thank you.